Hello, to warm myself up for interview week next week, or technically almost this week, I'll be doing a bunch of graph sketches and I will put the focus on explanations, communication, and most importantly, time. I have seven of these, so I should get started. Let me start with the first one, which is x squared plus x plus 1 times sine x squared plus 1. Now, the quadratic that's in the front of my graph is one that has no real roots, and I think that's quite important. It has no roots, and this part here determines my amplitude, and the part inside of my sine will determine the behavior of my period. I will start with scratching x squared plus x plus 1. This has, if I complete the square, this is going to be this. My turning point will be roughly here. So if I draw this, something like this, and y is equal to x squared plus x plus 1, and I will also draw the negative part of this because this quadratic will act like an envelope to my sinusoidal graph. I know that when when x equal to 0, my graph would be sine 1, which is roughly 0.84. So here, and what else can I say? The period, okay, the period will happen, a root will occur when the following is true. And this will happen. I'm going to use the general solution. And therefore, we have the following. And you can see that the square root graph looks like this, and it increases at a decreasing rate. So the roots will get closer and closer together. So my graph will look like something like this. I'm gonna try my best to draw it well. Let's say touches there, and so on. The periods get closer and closer and closer, and this goes up. And then we do the same here. And yeah, and so on. Okay, so that's the first graph done. I will check it after on Desmos. But I think this should be correct. Yeah, I don't see any big red flags with it. Okay, moving on to the next graph. It is y is equal to modulus x squared minus x times sine x. The same idea applies here. This will determine my amplitude, the behavior of my amplitude of my sinusoidal graph. So if I sketch this right, the period of my graph, of sine at least, it's normal in this case because there is nothing fancy inside the brackets. So I can expect this to be like a pi, 2 pi, and 3 pi, and so on. The modulus graph, this looks like the following. Actually, I'm just gonna draw as a root at x equals to 0 and x equals to 1. So this is what the quadratic would look like. But of course, we need to take the modulus of it. So it'll actually look like this. say it touches here. And what else? When x equals to 0, sine is 0, that's fine. So my turning point here should be x minus a half minus a quarter. And if I flip the turning point, it should be plus a quarter. Yeah. So, and what is this? This is 1, believe. Okay. So I would say my sine graph should look something like this. The period doesn't change. Well, I would say I need to reflect this as well. This might be a hard graph sketch. I'm gonna make sure my periods are spaced out evenly. Terrible sketch. And let's say it comes back here. And here would touch this, roughly something like this. What would happen here? I'm not sure. Let me see. The turning point happens at a half. So I'm gonna evaluate this. It's gonna be quarter minus a half, sine a half. I'm not sure what sine a half is. Um, well, it should be roughly sine a half. I'm not sure. Yeah. Okay, so this is going to be a negative number. Interesting. So my graph will look like something like this. And so on. Making sure that my periods are evenly spaced, which from my sketch isn't quite obvious, but if I state that, it should be fine. And this amplitude should be the same as this one. So more something like this. Okay. Next graph, y is equal to sine with the arguments x squared. Okay, this should be quite an easy one. Um, Now again, whatever's inside my, whatever is my argument is what determines the behavior of my period. So is equal to 0. I want to check where my roots are. Is equal to pi k for some integer x cube root of pi k. Now the graph of the cube root, what does that look like? The graph for cube root. Well, it can go in a negative because you can have negative cube roots. I'm not sure. I remember it looks like a lot like arctan, but not exactly. If I just try and sketch it right, would I be correct in saying it looks like something like this? Yeah, it should look like this. But regardless, I think the point here is that it increases at a decreasing rate, so my periods will get closer. My amplitude will stay the same, so I'm gonna say this is 1 and this is -1. The roots will look like this. And so on. We'll do the same here. Remember, sine x cubed should still be an odd function. Okay, this was horrible. Okay, and this should be my graph. Okay, good. Did I label my axis? I did. Next graph. What's in there? Sine. Oh no, no sine. It's a different graph. X plus one squared times e to the x. Okay. Y is equal to x plus one squared times e to the x. Okay. This graph will have a repeated root at x equals to minus one. That's my immediate observation. So I'm going to label that. So it's going to have a repeated root. Um, I'm going to sketch e to the x. So it's going to look something like that. And my x plus 1 squared graph should look like this. When does it cross the y-axis? When the x is equal to 0, so y is equal to 1. So it should cross the x-axis the same time the e to the x graph crosses the y-axis. So it's more something like this. This is quite an ugly sketch. So I'm gonna try to do it again. Yeah, like this, and so on. And my graph is going to be bounded by that. So I'm gonna change pen. So it's going to look something like this. Um, Perhaps it's taller here. So something like this. Okay, that's nice. And this is y equal to e to the x, and this is y is equal to x plus 1 squared. I think this should be correct. I don't know if there is a peak here. I should differentiate just to check my suspicion of turning point there is correct. E to the x plus 1. Well, just am I being stupid? This becomes 2x plus 2. Yes, this is correct. I was just checking. It's quite embarrassing. Very embarrassing on my part to have to check that thing. Okay, so this is my derivative. Means x plus 1 squared plus 2x plus 1 is equal to 0. X minus 1 is a root of this. Yes, and we already have that, so one turning point there. The other turning point is going to be and 16 minus 4 uh, 12 2 x is equal to minus 4 plus minus 16 minus 12 4 2 over 2. So our two roots are going to be x is equal to minus 8 over 2 minus 4, or x is equal to minus 1. Okay, so we've already got this one, and this should be minus 4. So yes, there's a turning point here and a turning point here. So this is roughly what my graph would look like. Nice. Next graph, How am I doing on time? I need to check that. Um, I am 15 minutes. What? 15 minutes. Shh. Oh my god. And I am okay. I've done this one. I've done this one. I've done this one. I've done this one. I'm gonna. Oh, I have like 3 graphs left. Shit. Okay. I should remember this. Ln x squared plus modulus x plus 1. Okay. Y is equal to ln x squared plus modulus x plus 1. So this is 2 different kind of graphs I need to consider. When x is bigger than 0, then this is y ln x squared plus x plus 1. When x is less than 0, y is equal to ln x squared minus x plus 1. I think this is the same one as before. This has no roots. We know that ln alpha is not defined when alpha is equal to 0, or and alpha is less than 0, so it can't be negative. Luckily enough, x squared plus x plus 1 is always positive, so we're not worried about that. So if I draw my graph here, for instance, this is going to be ln 1, and it's going to look like something like this. No, actually, I'm not exactly sure. I need to draw my graph. Yeah, it will look something like this. This was completely useless. Okay, x squared minus x plus 1. Believe this is has phi, the golden ratio as my roots. So it's undefined at the negative golden ratio root. So 1 minus root 5 over 2. I'm gonna approximate this to be should be roughly minus a half. Not sure, but I know somewhere here, and this is minus root 5 over 2. You can check that this is the root of this 1 minus root 5 over 2 is the root of this. I'm quite sure it is, if it isn't quite embarrassing for me. But still, well, okay. So the graph should look like, as it tends here, should go to infinity, because the behavior of the Len graph, as it tends to 0, is that it goes to tends to negative infinity. So actually, no, I'm wrong. It should look like this. And actually, I need to check when this is equal to 1, because len 1 is 0, x minus 1 is 0. So it's equal to, oh shit, no, the len 1 isn't, len 1 is 0, so this should look like this. Okay, okay, that was my mistake. Apologize for that. And this tends to infinity, and then it catches up again, and it should look like this. Okay, nice. I think this is going to be my last graph sketch I'll be doing, and right now I'll be checking on Desmos. Maybe if this video is well received, I shall do more graph sketches. Is there a way I can do this on Desmos, and you guys can see? Okay. Okay. Yes. I'm just gonna put Desmos on my recording. 1 second. I should be able to do this. Um, and I have, yes. Okay, I hope this can be seen. Okay, the first graph was X squared plus x plus 1 plus, times sine x squared plus 1, x squared plus x plus 1 times sine x squared plus 1. Okay, so this is roughly what I drew. Let me check. Yes, it is roughly what I drew. And if my hypothesis is right, if I sketch these separately, yes, this is bounded. My amplitude is bounded by this, and the negative version of this. Yes, I was right there too. Okay, good. And my periods decrease. Okay, so first graph, success. Second graph is modulus x squared minus x times sine x. Um, x squared minus x times sine x. Okay, this is slightly different. What did I draw? Okay, I drew something very odd. I think this part might be wrong, but if my hypothesis is right, yes, the amplitude is bounded by this graph. Oh yeah, I miscalculated. This should have been above the x-axis. Okay, my fault. That's probably the only mistake I did. But the rest is correct. The period stays the same, and my amplitude is determined by the maximum, or at least when it touches. The maximus are determined by when it touches the modulus x squared minus x graph. So next graph is, I would say this graph was still a success. Sine x squared. This should have been quite uncontroversial. Yep. Wait, was that x squared or x cubed? And what did I do? Oh, I sketched x cubed. Okay, okay, I see. I have copied this down wrong. But if I were to, okay, this is what I drew. Okay, everything is bounded between 1 and minus 1. Did I draw this? Okay, roughly. Yes, I basically drew that. And my, wait, I'm so confused. Yes, and my periods are getting closer and closer together. Okay, perhaps spotting that this should be more like this as opposed to a straight curve, and not sort of a curved curve. But yeah, I say this was success as well. The one I'm interested about is the next one: x plus 1 squared times e to the x. Um, x plus 1 all squared times e to the x. Ooh, interesting. And we do have a maxima at -3. Okay, I probably have messed this part out. Or did I copy the question wrong? Okay, my graph is not terribly far off. If I draw e to the x and x plus 1 squared. Yes, this part of my graph was correct. Oh, no, no. This should have been corrected. I will correct this now. Okay, this is terrible. Okay. And last graph was ln x squared plus modulus x plus 1. Ln x squared plus modulus x plus 1. Which looks like this. Okay, I think I've complicated things more than needed. If I look at my own graph, yeah, my own graph was not correct at all. Why? What are the roots? Surely, if I sketch minus x and plus x, I'm so confused. How can, because the first graph has roots and my quadratic can't be zero or negative. What? Oh, oh my god. Oh, both of them don't have roots. Oh, that makes sense. Oh, that makes sense. I see. Okay, so if I go back to OneNote, uh, well, I can't exactly for some odd reason. Yeah, okay. If I fix my mistakes, okay, the first graph was correct. Second graph, don't remember what went wrong. Not this went wrong. This should have been here. Okay, that's way too thick. I want to use this. This should be more like this. This was fine. My graph should have been more like this and more like this. This was my turning point. And I think something went wrong here and I've missed it because that's not my turning point. And my graph here should have looked like this because this does not have root phi, the golden ratio. Was it not? This has root golden ratio. I need to check this for my own sanity. Yes, 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 yes. And the golden ratio is like this. Okay, I even recalled this wrong. Okay, this is terrible. Okay, it's fine. This is a learning process. Considering this was time pressured, and I did how many graphs? Three, five under 15 minutes. Not terrible. Um, well, I guess I could have done better, and I'll be focusing on making sure that I talk more. I know it's very late in the night, and I should probably go to sleep because I have a philosophy to see tomorrow. So you know what? That's enough for today.